Hello, this is Wednesday's lecture for week 14. We're talking about chapter 30 and focusing on nuclear decay processes. Some notation that we're going to use: Z is the number of protons, N is the number of neutrons, and A is the sum of the two. And I imagine you're used to seeing this in your chemistry classes, but we use the big symbol in the middle for the chemical element, and upper left-hand corner is the total number of nucleons, and the lower left-hand corner is the number of protons. And there's some redundancy in this system because the element is uniquely identified by the number of protons in the nucleus. So quite often we'll leave out this subscript Z, and you can also write this as X-A. For example, carbon 12 would be 12 nucleons, 6 protons, and the symbol for atomic number of 6 is carbon. Okay, and then in table 30.1 of your book, there are some physical constants. You have the mass of a proton, the mass of a neutron, the mass of an electron. Notice that the mass of an electron is about 1,000 times less. And if you add up the proton and the electron mass, you get the mass of a hydrogen atom, which consists of a proton and an electron. And an atomic unit was defined so that a carbon-12 isotope is exactly 12U. And so it turns out that one atomic mass unit is this number of kilograms. And since we know that the rest mass energy is equal to mc squared, we have E equals mc squared. You can relate mass in atomic units to energy just by multiplying it by the speed of light. Okay, I just rewrote it there in fine tip. So energy equals mc squared, and you can just multiply this mass times 3 times 10 to the 8th, and you'll get this number of electron volts. Remembering that an electron volt is 1.6 times 10 to the minus 19th coulombs times volts. Okay, so binding energy, this is the thing that's responsible for nuclear explosions and nuclear power plants. We use the fact that the difference between the rest mass of all the nucleons that make up an atom and the rest mass of the atom itself is a positive number. So I guess what I'm saying is the bound version of the isotope has less mass than the sum of its parts. So this is an exception to the rule where the sum is greater than, or the whole is greater than the sum of its parts. It's actually less than the sum of its parts. And the difference is the binding energy that is released when you break apart that nucleus. Or for really low atomic numbers, that binding energy when you fuse light elements together. And so one of the things that's used in a fusion reactor is deuterium. Deuterium has one proton, but it also has a neutron, so it's kind of like a hydrogen atom, except it's got 2 nucleons in the nucleus. And its mass, its rest mass, is 2.014102. I know it's a lot of precision, but these numbers actually become important, especially when you're multiplying it by 1,000 mega electron volts per atomic unit. So when you take the mass of a hydrogen atom, so just using this figure for the mass of a hydrogen atom, times the number, times the atomic number, so in this case Z equals 1, plus the mass of a neutron, so I use this value for mass of a neutron. When I add those together and I subtract the rest mass of deuterium, I get a positive number. It's 2.2 mega electron volts per deuterium atom. Okay, next I'd like to talk about radioactivity. There's 3 different forms of radioactivity, and to say that probably you've heard about alpha, beta, and gamma radiation, but you know from your study of electricity and magnetism that this is not actually electromagnetic radiation except for photons. Alpha particles are just like bullets, right? But they're stopped by a piece of paper, so a helium atom. And a beta is actually an electron or a positron. We use the symbol E minus for an electron, the symbol E positive for a positron. The only difference between an electron and a positron is this is matter, so the everyday matter that we're acquainted to, and this is antimatter. When they get together, they annihilate and create a photon. In fact, that's the way to entangle photons. Okay, anyway, I'm getting off topic. So if we were to write this in a chemical reaction form, then the parent isotope, symbol X, and the daughter isotope, symbol Y, have this relationship. We know we have to conserve the total number of nucleons, and helium has 2 neutrons and 2 protons, which means we have to reduce the total number of nucleons by 4 and reduce the number of protons by 2. And similarly for beta decay, we turn a neutron into a proton or a proton into a neutron. So we change the atomic number by 1, either increase it or decrease it depending on whether we took a proton to a neutron or a neutron to a proton. And this little symbol that we've never talked about before is a neutrino. So this neutrino has no charge, but it's necessary to conserve the spin in this reaction. But we can, as far as the number of nucleons, number of protons, or number of neutrons, we can ignore it. And as far as the total charge, we can ignore it. But you'll notice here that since if we decrease the number of protons by 1, then we have to compensate for that by having the same number of positrons added. And similarly, if we increase the number of protons by 1, then we have to add an electron on this side. And finally, the gamma ray radiation is from an excited parent. So this asterisk means excited state, and you'll be entering the asterisk in your homework too when you mean excited. And the number of nucleons doesn't change, the number of protons doesn't change, the number of neutrons doesn't change, so A doesn't change. And so you have the same parent, same daughter and parent. It's just that the daughter is not excited and the parent is. And this is the symbol for a gamma ray or a photon. Okay, let's let n be the total number of radioactive nuclei. Then we can say that, just using people as an analogy, we know that the number of babies born at any time is proportional to the total number of people on the planet, right? So we can write dn dt equals minus some constant times the number. And here we're talking about radioactive nuclei, so the time rate of change of radioactive nuclei is proportional to the number of nuclei present, and the proportionality constant is called the decay constant, lambda. And by now you've seen this a couple times, right? We've used this in our description of voltage and current in capacitors and inductors, and so you know we can separate this and integrate it. We can divide both sides by n to get dn over n, multiply both sides by dt to get minus lambda dt. So everything that depends on t is on one side, everything that depends on n is on the other side. So then you can integrate both sides and you get this relationship for total number of nucleons as a function of time. And this looks familiar to you, right? Before, you've seen v equals v naught e to the minus t over tau, where tau is the time constant. So in this case, lambda, 1 over lambda, is our time constant. So we'll be using this for things like carbon dating, half-life calculations. So if we take the derivative, I guess I should go back. If we take the derivative of this expression with respect to time, so dn dt, that gives us the time rate of change of nucleons. That's equal to the rate. So we define this new term R for the decay rate. It's also known as activity. So the decay rate, if I take the first derivative of n with respect to time, it just brings the minus lambda in front. Yeah, okay. I ignored that minus sign. Yeah, it's the rate of decay, so it's implied that the rate is decreasing, but we don't actually put the negative sign to indicate a decrease in rate because it's always negative. And finally, another thing that you might have seen or heard about is half-life. And half-life is the amount of time that it takes the number of radioactive nuclides to decrease by a factor of 2. So in this expression, n equals n naught e to the minus lambda t, if I let n equals 1/2 n naught, then I have this expression. I divide both sides by n naught, then I take the natural log of both sides, and I get this, and you get that the half-life is log 2 divided by lambda. So this is how to relate lambda to half-life. And it's much more common to talk about radioactive isotopes in terms of their half-life, because right away it gives you a physical sense of what this means. oh, it takes 5,370 years for half of the carbon nuclides, half of the radioactive carbon-14 nuclides to disappear. That it's more tuned with our intuition than using using an exponential term. So, for example, let's find the activity R. R is activity of a sample after 8 hours, and the sample is the radioactive carbon, carbon-11. So let's say we have 3.5 micrograms of carbon, and we know that the half-life is 20.4 minutes. This reminds me of what we used to do on the submarine when we would, every once in a while, we would do background radiation surveys to determine how many radioactive particles we'd ingested. Usually, cobalt-60 from, well, I mean, there's lots of sources of radioactivity on a submarine, but we just wanted to make sure that we hadn't ingested any of this stuff. And so we did background surveys, and one of the things they told us not to do was not to eat bananas, because bananas have a radioactive isotope of potassium in them that has a similar half-life to this, about 20 minutes. So it's, decays very rapidly in your body, but it does have a very high R, and so that'll swamp any readings from cobalt-60. So anyway, back to this example. If we want to figure out the rate of this amount of carbon, first of all, we have to figure out how many nuclides we have. Well, we know that this 11 means there are 11 nucleons in the nucleus, so that means that it has a molar mass of about 11 grams per mole. And if I divide this mass by the molar mass, I get the number of moles. And then I just have to multiply by Avogadro's number to get the nuclei. So this gives me my number of nuclei, 2 times 10 to the 17th, roughly. And I have half-life. The half-life is 20.4 minutes, but in order to be able to do this calculation, this R equals n naught lambda, I need lambda. So I have to use this formula to convert my lambda, to convert my half-life into lambda. Here, if I multiply both sides by lambda and divide by t1 half, I get lambda equals log 2 divided by t1 half, so I get this expression. So now the log of 2 is 0.693 approximately. So if I divide that by 20.4 minutes and convert minutes to seconds, I get okay, 566 times 10 to the minus 6 inverse seconds. And then to find the rate, I have my n naught, which is 1.9 times 10 to the 17th, my lambda, which is this number. Well, here, I'll just say that. And then e to the minus my lambda again, times t. Okay, so after 8 hours, so that's 8 hours, and I have to convert hours to seconds. So 1 hour is 60 minutes, and 60 minutes per second gives me 3,600 seconds. I really don't like this. Okay, so I'm going to pause here while I plug that into my calculator. Okay, I just wrote this a little bit more neatly here. So just plugging these terms back into this equation for R, I get 8.9 times 10 to the 6th inverse seconds, where this number, 1.9 times 10 to the 17th, was the number of nuclei. So this number refers to decays per second. And a decay per second is the SI unit for radiation, called the becquerel, named after this guy, Henri Becquerel, who shared the Nobel Prize with Pierre and Marie Curie in 1903. Okay, the last subject I wanted to talk about is carbon date. Wait, have I covered everything? Yeah, I think I talked about all the decays, right? Yes. Okay, so the last topic is carbon dating, and carbon dating has kind of come under attack by the religious right because it implies a form of faith. Well, the form of faith that we're talking about is this probabilistic event that happens is, nuclear decay is a probabilistic event. We can just say that there's some probability that an atom will decay in a given time. But we do have a good idea statistically of how long it takes for example, for half of the population to decay. So that's been tested over and over again experimentally. And so the carbon dating is based on this fact, and that is that the way that carbon-14 is made is from cosmic ray radiation, and it turns out that the proportion of radioactive carbon-14 to carbon-12 in the atmosphere and in all living beings on Earth, because living beings exchange carbon dioxide with the atmosphere all the time, is 1.3 times 10 to the minus 12. So a very small fraction of the carbon around us is carbon-14. But it's still very useful because it sticks around for a long time. The half-life for carbon-14 is 5,730 years. So what makes this cool is once an organism stops living, it stops exchanging carbon with carbon dioxide with the atmosphere. And so the amount of radioactive carbon-14 that's in the sample at the time of death is the amount of carbon-14 that you see now adjusted for decay. So all we have to do is figure out the ratio, figure out the decay rate of the sample that you have now, and see how many half-lives have elapsed. So I'd like to look at this example. For example, let's say you're Indiana Jones and you find an old ruin, and the ruin has a piece of charcoal from a tree. So you've got a 25-gram sample. Charcoal is just carbon, and it's got an activity, R, of 250 decays per minute. So we're going to have to remember, I need to convert this to decays per second to use the SI unit. And the question is, how long has the tree been dead? So just starting from our rate equation, R equals R naught e to the minus lambda t, I want to know what is the time. What is the time, and because I'll be able to find lambda given my half-life, when the decay rate R over R naught is this ratio. And I know R naught because I know the activity level of this amount of carbon-14, and I can compare that to the R that I have right now to get lambda. We can find T. So to find lambda, I just take the log of 2 divided by the half-life, and I convert this, if I want, just to be consistent with Becquerel, which is decays per second, I turn this into seconds. So this 3.156 times 10 to the 7th is just 365.25. So 365 and a quarter days per year times 24 times 24 hours per day times 60 minutes per hour times 60 seconds per minute, and you get this number. So this gives me a very small number for lambda. And then remember our rate, when we were determining rate, it's just the first derivative of n, and n equals n naught e to the minus lambda t. So when you take that derivative, you get a lambda because you have a lambda in the exponent. So this is my R naught term. So the original number of nucleons times lambda. This is what I have in brackets here is the number of nucleons. How do you figure that out? Well, you've got a 25-gram sample of charcoal, carbon, and you know that the molar mass is 12 grams per mole, so 25 grams divided by 12 grams per mole gives me the number of moles. So if I multiply that by Avogadro's constant, 6.02 times 10 to the 23rd, that gives me the number of nucleons. But the only nucleons that contribute to the radioactive decay process are the radioactive carbon-14 ones. And I know that the ratio of carbon-14 to carbon is 1.3 times 10 to the minus 12th. So that means I have to take this number of moles of carbon, multiply it by this 1.3 times 10 to the minus 12. That'll give me the number of carbon-14 nucleons. And so then all that's left is multiplying that by my lambda, and I get 6.247 Becquerel. So that's decays per second. And our given, it says the rate right now, the rate today is 250 decays per minute, and if I convert that to Becquerel, I just divide by 60 seconds, and I get 4.16 Becquerel. So the only thing that's left to do now is to use this relationship to, this to find T. So let's try that. Let's see, lambda is Yeah, okay. Well, alright, that's fine. I'm going to have to convert this into years at the end. I was going to say, let's just use lambda in terms of our, just keep it in terms of years. But anyway, I went down this road, so I'll just finish it. Times the log of r over r naught. So 4. My Becquerel units cancel, so I won't write those down. Okay, I'm going to plug this into my calculator now. Okay, so when I plug all that in, I get 105.7 times 10 to the 9 seconds, and I divide that by 3.156 times 10 to the 7 seconds per year, and I get 3,350 years. Great, so that completes the lecture for today. Thanks for your attention. If you have any questions, please don't hesitate to text or email.